Please title these notes Derivatives 2 Notes, Introduction to Calculus, and write today's date. Please start by writing what you see here. By the end of this lesson, you should be able to describe the differences between precalculus and calculus, define the derivative and integral geometrically and in terms of change, and also estimate the derivative and the integral from a graph. Calculus was an incredibly powerful tool that was developed in the 1600s by Sir Isaac Newton and Gottfried Leibniz as a way to more quickly and easily solve a host of mathematical problems that were challenging Enlightenment mathematicians. Before the development of calculus, geometry and algebra allowed mathematicians to work with idealized, unchanging shapes and concepts. However, the real world is a lot more complicated, and mathematicians needed tools that would let them analyze messy, changing mathematical objects. So what calculus really is it's really the mathematics of change. And we're going to start off by doing a little table showing precalculus versus calculus, how they're similar and how they're different. So precalculus, these are idealized, unchanging objects. Whereas calculus deals with more realistic, changing objects. And objects here can mean anything. It can be a concept, it can be a shape, anything. So in a similar vein, precalculus is dealing only with the slope of a straight line. So for example, if we have a little line going off like this, then we know that from one point to another point, this distance we call the change in y. This distance we call the change in x. And then we know that the slope of the line, a change in y, over change in x. Change in is an awfully long thing to write, so this is sometimes also notated as delta y and delta x, with the delta meaning change in. We know this all the way back from Algebra 1 as rise over run, same idea, rate of change. However, calculus deals instead of with the slopes of straight lines with the slopes of curves. So for example, imagine we have something like this. At this point right here, we're trying to figure out what the slope of the curve is. And we can't do change in y, change in x the same way we did here because we can see that this is curved. The slope is changing as we go along the curve. This single point is so small that we can sort of imagine sort of an infinitely small change in y over change in x right here. But we can't really see it. What we have to do is sort of expand this curve and sort of continue it as if it were a straight line. This is called a tangent line. And once we have that tangent line, now we can actually see our change in y over change in x again. The idea is the same for finding the slope of a curve as it is for finding the slope of the line. The difference is that in calculus, the changes in x and the changes in y are infinitely small. These infinitesimal changes that are actually called differentials with a D, have their own notation. They're sort of a dy and a dx. And so when we're looking for the slope of a curve, at a particular point, it's still change in y, over change in x, but it's now the changes in the tangent line. This is going to be notated dy dx. Delta over here is the Greek letter for d. This is an uppercase delta. So a lowercase d is basically saying we're representing the same concept, just a lot smaller. Okay, another change for calculus versus precalculus. Precalculus deals with a constant, or average, speed of motion. Calculus deals with varying, or instantaneous, speed of motion. So if we imagine that we have a little person here, and this little person is running along, in precalculus, what we can do is we can find their average speed by saying from this point, I'll figure out what their position was and what time it was at this point. And then we say, okay, I'm going to find their time and their position at this point. And I'm going to find their average speed by finding change in position over change in time. In calculus, we've got the same little person running along, but now we can find their instantaneous speed using something called the derivative. And I'm going to write down this symbol here. We're going to learn what it means later on. It's not going to make a ton of sense right now, but that's okay. We're just going to be using the derivative to find at a single instant what's their speed at that instant, rather than having to figure out average speed over a length of time. It's again that idea of being instant. So this is how fast the runner's position is changing at that instant. The final piece is that precalculus allows us to find the area and volume of regular figures So that's like finding the area of a circle, pi r squared, finding the area of a triangle, 1/2 base times height, finding the area of a rectangle or a square, length times width. Those basic formulas that we've worked with. Calculus, however, lets us find the area and volume of irregular figures. So for example, let's say we've got this really weird shape and we've got some function for it, f of x, and this is x, and we want to find the area under this shape from A to B. Calculus permits us to find this weirdo funky area using something called the integral. And there will be more on this notation coming later. But this is the basic idea, repeated over and over, is that precalculus lets us do these sort of idealized, not very realistic things, whereas calculus permits us to do much, much more in terms of working with the real world and working with things that are varying and changing and irregular. The new tools that calculus developed were so powerful that much of science and mathematics in the 1700s was basically just finding new ways to apply two really basic, when you get down to it, concepts. So let's look at the two main branches of calculus and what they're used for. Calculus is really just two main ideas. There are a lot of other things behind them and going into them, but really we're just going to be mostly talking over the course of the year about something called the derivative and the integral. Let's first give you the notation for each. The derivative can be notated several different ways. Gottfried and Leibniz and Isaac Newton both developed their work somewhat independently, and they used very different notation for it. And today we still use some different notations for the derivative, but basically both of them, or all three of them, are more convenient at different times, so they've still persisted today. So this is read as d dx of f of x. This is dy dx. And this is f prime. That little symbol isn't a 1, it's a prime of x. These all mean the same thing. They all mean the derivative. And we're going to talk about what the derivative is soon. The integral really only has one notation that's left at this point. This would be read the integral or the antiderivative of f of x dx. We're going to start with the geometric notation, or excuse me, the geometric definition. Of each of these. So the derivative is the slope of the line tangent to a curve at a given point. So to draw a picture of that, this is f of x, this is x. We have some funky little curve here. The tangent line separate that out so you can see it a little better, is the line that just brushes the curve at the given point. And all the derivative is the slope of this line, just like we were working with when we were talking about the differences between calculus and precalculus on the previous page. The integral is the area, so this is area instead of slope, bounded by the graph of a function from x equals a to x equals b. Notice that the derivative is taking place at a point, whereas the integral is from one to another value of x. So, sketch that, x, f of x. We've got our little funky curvy shape. The area under the curve from a to b, whatever value of x, a, and b are, area under the curve, or the area bounded by the curve, these two lines, and the x-axis. So really when we're looking at integral, we're talking about area. When we're looking at the derivative, we're talking about slope. Those are the two basic ideas in calculus, and they're also the ones that we were talking about on the previous page. So let's do a couple of examples where you're just going to identify whether or not we're working with the derivative or the integral, and then estimate what the values of those are. So right below here, let's write examples. First, on the curve at right, sketch a line tangent to the curve at x equals 1. So here's a little graph of what we're going to be working with. You can grab some graph paper, do a little sketch of this, or if you can put up the paper up to the computer screen and sketch it off there. When I give you homework problems, I'm going to give them to you on graph paper, so you want to get the idea from this. Sorry, this should be x equals 4. Tangent to the curve at x equals 4. So the idea with the tangent line is we want to just barely brush this curve. And we want to do it right at where x equals 4. So that's this point right here, x equals 4. By coincidence, y also equals 4, but I'm looking specifically at x there. And so what I'm going to do is grab a straight edge and basically try to take that straight edge and put it where it just barely brushes that curve. So about like that. This is going to be an estimate. So if it ends up a little bit differently, that's okay. But there we go. I've just sketched a little tangent line right there. Now what I want to do is I want to estimate the slope of the tangent line. The slope is change in y over change in x. So here's my little line. I'm going to take 1 point here, 1 point here. I could have picked these points. It's whatever, it's fine. Change in y, I went down 2. Change in x, I went right 1. So change in y over change in x is negative 2 over 1. Negative 2. Notice it's sloping down, so it's going to be a negative slope. And then C, have you found the integral or derivative? We know that the slope of the tangent line is associated with the derivative. So that means we've found the derivative of, this is called f of x, at x equals 4. And there we go. That's calculus. There will, of course, be a lot more to it, but that's the basic idea. Okay, let's do another one, working with the integral this time. On the curve at right, shade the area under the curve. You'll see this phrase under the curve a lot. It really means bounded by the curve and the x-axis from x equals 3 to x equals 5. Let's make that x equals 6 for kicks. 6. There we go. Okay, so the area under the curve, from the curve to the x-axis, from x equals 3 right here to where x equals 6 right there, we're talking about this area right in there. And now, similar to what we were doing before, let's estimate this area by counting squares. So this means you might not come up with the exact same number that I do, but it should be in the right general vicinity. So each square is 1 unit wide by 1 unit high, so it's 1 square unit right here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 little squares. And you can see these if I go and draw them back in again, because I got a little covered over when I was doing the shading. You can see there 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we've got 12 whole squares. And then up here we can see we've got part of squares. So it looks like there's about half a square there. There's about half a square there. There's a little more than half a square there. So I'm going to say that we've got our 12 here. This one and this one, probably when we put them together, that's about another square, so that's 13 total squares. And then this looks like more than a square, or more than half a square, so call it 13.6, 13.7, 13.8, somewhere between 13 and 14 little squares. Really between probably about 13.5 and 14. So that's all that is. That's estimating. That's the basic idea of what we're doing, just finding the area under the curve for calculus. And then let's ask, did you find the integral or derivative? Remember from the previous page, the area under the curve is associated with the integral. So that means that we found the integral of, this is f of x again, from x equals 3, that's where we started, to x equals 6. That's where we ended. Notice that the derivative is at a single number. The integral is from one number for x to another number for x. In addition to defining the derivative and the integral in terms of geometry, we can also define them in terms of change. So these are notes again instead of examples. This is derivative and integral. And now we're going to give the change definition. The derivative is the instantaneous rate of change of a function. The most easy to comprehend change that we have is in terms of velocity and position. So let's say we imagine so we know a person's position over time how fast is their position changing at a particular instant. So this would be called also, what is their instantaneous velocity? And especially for these practical problems, it's going to be really important to have the units. These units are always going to be the y-axis units divided by the x-axis units. And this is because slope, which remember is associated with the derivative, is divided x. So a helpful way to visualize this is using an example of a person moving back and forth. This is over time, so the blue graph right here, that's giving us position on this little ruler here. So like right there, he's at 0 meters, he's at 0 on the position graph. Velocity is that little red arrow that we're looking at right here. It's just how fast is he moving? What's his velocity in meters per second as he goes along? This green graph is acceleration, although we're not going to be working with it right now. So what we want to know is we want to know what's moving man's instantaneous velocity, what's his rate of change of position, let's say when he hits this tree. So he's going along, basically this little velocity that's tracking his change in position over change in time. That's really what the derivative of position is, its velocity, and then right there when he hits the tree, just a little bit further, right there when he hits the tree, if we want to know what his change in position is, his instantaneous velocity at this point, we can look right down here in the blue. Let's move him back just a little bit. There we go. What's the slope of the tangent line to the blue curve right now? Well, it looks like it's going to be a flat line, slope of 0. And lo and behold, when we look on the velocity graph, right there, the value of the velocity graph is 0. So when we're talking about a derivative as a rate of change, this is what we're talking about. We have his position in meters. The derivative is his change in position, meters per second, his velocity. The integral goes the other way. If we have a function that gives a rate of change, the integral is the accumulation of that change. So to give an example using moving man again, if we know a person's velocity over time, what is their total change in position? This is also saying distance traveled. And the units for this, they're going to be the y-axis units times the x-axis units. And this is because area is height, which is y, times base, which is x. Looking back at moving man, What we're really looking at here, instead of going from position to velocity, is we know something about moving man's velocity. What's his total change in position? So velocity is a rate. Let's say like right here, from 12 seconds to 14 seconds. I know right here on this red graph that moving man is moving at 3.5 meters per second for these 2 seconds. So that means that over the course of these 2 seconds, if we find the area under this curve, so this width is 2, this height is 3.5, so this area right here is 7, that means that his change in position should be positive 7 meters. And lo and behold, if we look at what his position is at 14 seconds, ta-da! He's gone an additional 7 meters. So the idea with the integral is that if we know this rate of change over how long that rate of change has been going on for, then that'll give us the total change up here on the position graph. You can see that the integral and the derivative are very tightly linked. Basically, one goes from position to velocity, the other from velocity to position. And in fact, they are very tightly linked. The derivative and the integral are inverses. Meaning they undo each other. Just like multiplication and division are inverses. Let's look at some examples using this change definition. So here we have a graph of velocity. And given this velocity graph, would you use the derivative or the integral to estimate the distance traveled from 5 to 7 seconds? So take a minute to think about that. What do you think? We will be using the integral because remember, velocity is giving us a rate of change, so meters per second. We know that distance is in meters, so to get back to meters we're going to be taking the integral, getting back to the total change, the total distance traveled. So we'll be using the integral. On the graph, we want to draw a geometric representation of the distance traveled. Remember, this is the integral we said right up here. So go ahead, draw something on here that represents the integral from 5 to 7. Remember, the integral is the area under the curve, so we're looking at the area under the curve from 5 to 7. Now we want to estimate the distance traveled. So the distance traveled was the integral, was the area under the curve from 5 to 7. So we're just going to divide that up into little boxes just like we did before. Use that to estimate. So we've got 1, 2, 3, 4, 5 little boxes. And then this is a little less than half a box. That's a little less than half a box. So if we put these together, we're going to be almost to 6, but not quite. So approximately, let's call it 5.8 or something like that. Really, we could say probably anywhere between probably about 5.5 to probably 6.5, somewhere in there. It's sort of an approximation. However, it's going to be very, very important to have the units. So this is area. Units are going to be meters per second times seconds. Seconds cancel out. Or approximately 5.8 meters. For this next example, I'd like you to take a look at it and then pause the video and try to do it on your own. When you're ready, start the video again and I'll show you the answers that I have. Go ahead and pause the video now. Okay, so to estimate the rate of change, so the keyword here is rate of change of velocity with respect to time at t equals 4 seconds to use the integral or derivative. Remember from what we were working with earlier that rate of change right here, we're looking at the derivative. So this would be the derivative. The derivative is represented by the slope of the tangent line. So we're going to draw a tangent line at t equals 4 seconds. So t equals 4 right here. Draw a line that just brushes. Something like that. Now notice that yours might have been a little more tilted up, a little more tilted down. That's why we're going to spend a whole year working on this stuff so that we can get this really precise. But for now, we just want an estimate. So we're going to estimate the slope of this line for part C. Change in y is 1. Change in x is 1. So we're looking for slope. Change in y over change in x approximately equals 1 over 1 or 1. Now, this could be anywhere between 0.5 to, with these it's actually really hard to tell. So as long as it's positive and it's not too big, it's going to be fine. However, we need to make sure that we have units. So the units are going to be y units, meters per second, divided by, because we're doing division over here, divided by seconds. This is the same as seconds over 1, so it's 1 meter per second. Dividing by a fraction is the same as multiplying by a reciprocal. So there are 2 seconds in the bottom, 1 meter per second squared. Those are the units for acceleration, incidentally, which, if we looked at the moving man example, was the next level down from velocity. That makes a certain amount of sense. But this is what we're looking at when we're finding our units. Slope, derivative, we're going to do the y units divided by the x units. Up here, area, multiply the 2 units. Okay, 2 more examples and then we're all done. For this one, on a graph of v of t over here, sketch a geometric representation of v prime of 3. Is this the integral or the derivative? And before I tell you, I'd like you to take just a second to glance back in your notes and see if you can figure that out. I haven't told you yet, but you might be able to put it together. So pause the video for a second, see if you can figure it out. Okay. The relevant piece in your notes is right over here where we looked at these notations. Notice the little prime. That shows up over here. This is the little funky S shape. It's actually a summa. It means to add up. And one of the things that we've mentioned several times throughout the notes is that the derivative always takes place at a particular value. So if all I'm telling you is that we've got v prime, we've got a little prime, and I've got a number, what this is really saying is it's saying we're looking for the derivative at, well, there's only one number we've got, so it's got to be that one, x equals 3. So the derivative at x equals 3 means we can find 3 for x, and then we sketch that little tangent line. So this is a horizontal line right there. What real-world concept does v prime of 3 represent? Again, pause the video for a second and see if you can figure it out. Well, real-world concept, that's not talking about geometry, that's talking about the rate of change. So the derivative is the instantaneous rate of change of a function. So this is the rate of change of velocity. And again, we have that 3 at, whoops, this should be t. This should also be t. T equals 3. And so now we want to estimate v prime of 3. So this means estimate slope of tangent line. This is a flat line. There is no rise. There is no change in y. So that means 0 divided by anything is just 0. It does still, however, have units. So remember that our units are going to be miles per hour divided by hours, or miles per hour squared. So I kind of put this in here, so it's getting a little messy there, but v prime of 3 approximately equals 0 miles per hour squared. Okay, last problem here. So also looking on a graph of velocity, sketch a geometric representation of this right here. Is it the integral or the derivative? Take a second to look up whether or not you think it's integral or derivative, and then I'll tell you how to pronounce this. So this is, in point of fact, the integral. And all that you saw in the notes is that the integral is just that little symbol right there. This is new because there are the little numbers here. However, we know that the integral is associated with the area under the curve. And we have to have the area under the curve between two numbers. So that would kind of logically imply that that's what these numbers are. They're the only two numbers we've got. So we're probably looking at the area under the curve between 1 and 4. And indeed, that's what this means. It means the integral of phi of t from t equals 1 to t equals 4. Right there, from 1 to 4. So what real-world concept does this represent? Well, when we looked at our real-world explanations, we're given a function that involves a rate of change. So velocity is the rate of change of position. So the integral is the accumulation of that change. So if we know a person's velocity, looking at their change in position. So this represents total change in position from 1 to 4 seconds. And now we want to estimate that. Okay, so we've got 1, 2, 3, 4, 5, 6, 7, 8 whole squares. And then this one's a little bit more than half a square. That's a little bit more than half a square. That's a little bit more than half a square. So if we put them all together, then these two together are going to make a 9th plus a little bit. And when we put all this together, we're probably talking about 10. Now, looking again at the units, this is area, so we're going to do miles per hour times hours, 10 miles. And again, we're probably looking at anywhere between 9 and 11 miles for an estimate. Okay, this concludes these notes.